So we're going to analyze a compound circuit. We've already talked about parallel circuits where the electricity has different paths to go through. And we've talked about series circuits where the electricity only has one path to go through. And now we're going to talk about a compound circuit where the electricity has multiple paths to go through. So it is a combination of series and parallel circuits. And we have one here where the electricity comes out of this 18-volt battery and it goes through, it all has to go through resistor 1, and then it has a choice. It splits, and it can either go through just this one resistor 5 here, or it can go through this series of 3, meet back up with the electricity that went through this resistor, and then all pass through resistor 6 back to the end of the battery. Okay? But what we're going to do is we're going to do the break it down and build it back up system. So we're going to break this down into one equivalent resistor. So the resistance that the battery feels in total due to all of these, and find the total current passing through the system, and then we'll build it back up. We'll build it back into this original thing, and we'll find the current and the voltage at each and every resistor. And the way we start with this is, it's always nice to just sort of take it in like you're pulling it apart, pulling the battery apart and stretching it out. So we're going to redraw it. Follow along with me here for a second. So we're going to start with our 18-volt positive end of our battery. And here, the electricity has to go up, and it has to pass through R1, a 5-ohm resistor. But then it gets to this junction, we'll call it 1, where it has a choice of either going through this single, we'll call R5, 3-ohm resistor, or it can pass through this series, R2, 3, and 4, R2, 3, and 4. So R2 is 4 ohms, R3 is 2 ohms, and R4 is 1 ohm, where it then meets up with at junction 2 with the electricity that passed through resistor 4. Then it all goes and passes through resistor 6, a 5-ohm resistor, to the end of the battery. So I've just redrawn this in a line. Okay? And now I'm going to look for ways to combine resistors all the way down till I have just one resistor, an equivalent total resistance that the battery feels. And the way I can do that is by using these two equations, that for series circuits, you just add the resistors, and for parallel circuits, you add the reciprocals of the resistors. But I can't do them together. I can't just add reciprocals and individual. I have to take care of things that are in series first by themselves and things that are parallel by themselves. And if you look here, I can't do one. I can't combine it with anything because everything is a combination of series and parallel. I can't do 3 with anything because it's in parallel with the series. I can't do 6 to anything. I can't add it up because it's connected to this series that's also in parallel with this. The only ones I can combine first are these 3 things that are in series. Okay, so I'm going to redraw it again. My 18-volt positive is going to go through resistor 1. And then it's at junction 1, I'm going to add all of these series resistors here, and I'm going to call it resistor 2, 3, 4. And it's 4 plus 2 plus 1 is a 7-ohm resistor. So these 3 add up and all act like a single 7-ohm resistor. Okay, and I'm going to redraw resistor 5, my 3-ohm resistor. It's going to join up at 2, and it's all going to pass through resistor 6, a 5-ohm resistor. Now, I'm going to see if there's anything else, if I have at least 2 resistors that I can combine into one. And here I have these 2, they're nothing but parallel, so I'm going to redraw this as the electricity going through resistor 1, a 5-ohm resistor, and then right here I'm going to use my reciprocals equation, reciprocal for parallel circuits, and I'm going to find the equivalent resistance. I'm going to add these 2 into one resistor that I'm going to call resistor 2, 3, 4, 5, and I'll do that by it would be 1 over 7 plus 1 over 3. So I'll get out my calculator and I'll find the reciprocals. And then I'll take the reciprocal of that. And it says the whole thing is 2.9 ohms. So this 7 ohm resistor and this 3 ohm resistor in parallel act like one single 2.9 ohm resistor. Okay, and then here it still all has to pass through resistor 6, a 5 ohm resistor. Now I'm going to keep going. Now all I have left are 3 resistors in series, so I know that I can just add them into one equivalent resistor that I'm going to call resistor 1 through 6. And it's 5 plus 2.9 plus 5, so it's a 12.9 ohm resistor. So up here, the electricity passing through all 6 of these resistors, the battery feels a combined total resistance of 12.9 ohms. Okay? And now that I have it down to my total equivalent resistance is 12.9 ohms, I'm going to solve for my total current using Ohm's law. Okay? So I know that Ohm's law says that the current is the voltage over the resistance. So the total voltage is 18 volts over the total resistance is 12.9 ohms. So 18 divided by 12.9 is 1.4 amps. So this circuit feels a total of 1.4 amps moving through 12.9 ohms of resistance. So 1.4 amps is the total equivalent current. Now what I'm going to do is that we tore it down to one equivalent. We found the total current and total resistance for my 18-volt system, and I'm going to go back up through and build it back up to the original, finding the current and the voltage at each and every resistor, all the way back along the line. So let's do this one here. So I know that for series, if I read up here, that for series circuits, current is the same everywhere. And this one, this one equivalent resistance is being broken up into these 3 in series. Since all the electricity must pass through, since the current is 1.4 through here, the current is 1.4 amps through all of them. And now, I don't know what the voltage is, but I can figure it out because I know from Ohm's law that voltage is current times resistance, and I have current and resistance. So voltage is 1.4 times 5, or 7 volts. And look, these are the same. They're both 5 ohms, and they're both 1.4 current. So this one, the voltage is also 7 volts. And here, voltage is still current times resistance, so it's 1.4 times 2.9. So I'll get out my calculator, and I'll go 1.4 times 2.9, and I get that it's 4.06. We'll just say 4 volts. Now look, this is key. So we're looking to when we get back to the original resistors, and if you look, 1 and 6 are now completely separated. They are not a combination of anything. This is resistor 6 by itself. This is resistor 1 by itself. So I can go back up and fill up my chart. I know the current is 1.4 at both of them. So the current at resistor 1 is 1.4 amps. And the current at resistor, sorry I didn't put resistor 6 on here, is also 1.4 amps. Okay. And I know the voltage is 7 volts at both of them. So it's resistor 1 is 7 volts. And sorry again, I didn't put 6 on there. Is also 7 volts. Not 7.4, 7 volts. Okay, and now I'm going to keep going. I'm done with 1 and 6, so I don't have to worry about them anymore. But this one resistor, this compilation of resistors 2, 3, 4, and 5, has a total resistance of 2 ohms and a current of 1.4 amps and a voltage of 4 volts. And I'm going to take that into what it was before, the step before, which was these two, this combination of 2, 3, and 4, and 5 in parallel. And I know for parallel circuits, voltage is the same. So if the voltage was 4 volts here, then I know the voltage is 4 volts there, and the voltage is 4 volts there because it's the same in parallel. And now I can figure out the current because current is voltage over resistance, so it's 4 volts over 3 ohms or 1.3 repeating amps. And up here, current is voltage over resistance, so it's 4 volts over 7 ohms, so that's 0.57 amps. Okay, and here we go again. 5 is done. I'm all done with 5, so I'm not going to have to worry about it again. I know the current on 5 is 1.3 amps, so the current at 5 is 1.3 amps, and I know the voltage at 5 is 4 volts. Okay, and now, so I'm at this step, and I have this one equivalent resistor, equivalent for 2, 3, and 4. So I'm going back up to where it's in series, and I know that for series circuits, current is the same. So if the current was 0.57 amps through this combination here, then the current is 0.57 amps for all of them. Okay, which allows me to solve for, because I have resistance and current, I can solve for voltage. It's current times resistance. So 0.57 times 4 is 2.3 volts. And in here, voltage is current times resistance, so it's 0.57 times 2, so we'll say 1.1 volts. And here, 0.57 times 1, so current is 0.57, or a voltage is 0.57 volts. So I can go ahead, I know that resistor 2, the current is 0.57, and the voltage is 2.3. And at resistor 2, I know the current is 0.57, and the voltage is 1.1 volts. And at resistor 4, I know that the current is 0.57 amps, and I know that the voltage is 0.57 volts. And you can check, I know the total voltage is 18. I can add all these up. 7, 7 is 14, maybe 16.3, 17.4. I'm trying to add all this up. And we can also check the total current. But here we found the current and the voltage at each and every resistor, and that's called analyzing a circuit. And of course this happens for like computers. If you want to be a computer designer or a chip designer that has billions of circuits, you have to be able to know what the current and voltage is at each and every little resistor in it.